Hi, my name is Lauren Champney, and the article I'm going to be discussing is avian vision models and field experiments determine the survival value of peppered moth camouflage. The article is written by Olivia C. Walton and Martin Stevens, and they conducted their research in 2018. Sorry. So I'm first going to start out by showing or giving a little background information. So there's two different colors of the peppered moth that exist in the wild, and I will show you those right now. The first is the dark melanic peppered moth, which is the one up top. It is darker in color and it is better suited for bark with nothing on it. So just plain bark. And the second is the pale peppered moth, which is here on the bottom, and it is more suited for bark that is covered in lichen so that it can camouflage and blend in more closely to that and avoid predation. So during the Industrial Revolution, when pollution was really high in the atmosphere, trees began to be covered in a layer of soot, which made their appearance a lot darker and killed off the lichen that was on any of the trees. So, as expected, when this happened, the frequency of the dark peppered moth in the population was a lot higher than the pale peppered moth because, at an evolutionary standpoint, they were able to escape predation at higher rates than the pale peppered moths. And then after the introduction of the Clean Air Act, which happened in 1950, the rules were reversed. So lichen started growing back on the trees. And when that happened, the pale moths were able to survive more suitably in the environment compared to the dark peppered moths. So the first person to do research on the peppered moth was Bernard Kettlewell, and he conducted his research in England in 1953. He worked in a polluted woodland area, and there he found that the frequency and the number of the dark peppered moths was a lot higher than the pale peppered moths. And then in 1955, he conducted research in a clean forest where he found the same thing. The frequency of the pale peppered moths was higher than the dark peppered moth. So the researchers in this article thought a little bit differently than people typically did when working with the peppered moth. They wanted to take into account what the birds actually saw rather than what the people saw, because they recognized that birds have a different number of receptor types. They have different receptor sensitivity in their eyes, and they're also able to see UV light. So they thought maybe some of these factors had to do a little bit about their camouflage patterns as well in the peppered moth. So the first study they conducted was to see how closely their camouflage matched their suited environment. So, for example, they wanted to see how closely the dark peppered moth matched just plain bark and how closely the pale one matched the bark with lichen on it. So, when they did such, they used museum specimen and took digital images of those specimen, which is actually kind of cool because they got to use actual specimen from the original research done by Bernard Kettlewell. So they used digital image analysis and model avian, so bird vision, to kind of create these points right here. They deem them as just noticeable differences. And they state that when the just noticeable difference is close to one, that suggests that the camouflage is so effective that the colors cannot be distinguished. between the moths and their resting background. And here are the results of that experiment. So the dark line represents the mean just notable differences in each of the different moths and in different environments. So as you can see, the dark line, and then the dashed line represents the min and max values, and the circles are just outlier points. The top graph, graph A, you can see is the color just noticeable differences, so just in the color, and then the second uses the luminance just notable differences, which takes into the account the birds being able to see in UV, see UV light, see the reflections of the UV rather than just the visible light spectrum. And their results coincided with their prediction that each of the different moths would be more effectively camouflaged in their area. So for example, they expected the dark moth to be better in the plain bark and vice versa. They did note that the pale moth was a little bit more effectively camouflaged. As you can see, its mean average bar is a lot closer to 1 than that of the melanic, but they still were able to get their point across that from a visual standpoint, their camouflage was effective, and overall that helps them to escape predation. Their second experiment was conducted using artificial, oh, I forgot to mention for the last one, oh no, I did say that. They got their specimens from the museum and then they got the specimens from the museum and used images like that, and they kind of repeated that with 65 different like versions of each of their wing color. And then the second experiment was that they wanted to see how well each of the moths could survive in an unpolluted wood. So what they did here was they generated 50 different individuals of each color, so 50 of the pale ones, 50 of the dark ones, and they made artificial prey out of them precisely. So they did the same thing. They got good analysis of their wing color and then printed them out on a printer, making sure that the size of the wings, the size of the body were the exact same. And then they put a center full of paste and then hung them all up in their respective areas and observed them for 48 hours to see which one was camouflaging better. The results of that experiment came in that the plain, the pale peppered moth was about 23% greater at surviving the 48-hour period compared to the dark melanic moth, and that is because they were in an unpolluted area where the lichen had grown on the trees. Some important things to consider when talking about that experiment is that they didn't put the dark moth in its environment that it is suited for, and they never tested to see the suit and how well, I guess this is for both experiments, they never put the suit on the tree or the soot on the tree because they didn't know what patterns it did during the Industrial Revolution and how it fell on the trees, how thick it was. So they didn't want to kind of compose that information without being exactly sure because they didn't really want to fabricate anything. So instead, they just used the plain bark, which could be why the pale peppered moth seems to be so much better suited for the environment because this isn't the environment it was in during the Industrial Revolution. So something interesting about this article is that most of the analysis and everything was done on computers, and without the technological advantages that are done now, such as the digital imaging analysis, the different softwares that they use to make the matches would not be possible. So that is something to consider when looking into this article. Um, I also thought it was interesting how there was no conclusion in this article, and I was kind of curious about the artificial moths because they're not able to escape predation anyway because they're just pinned to a tree rather than, I mean, they could probably try to fly away if they were real moths, but using artificial moths, they're unable to escape the predation. So I was wondering if that could have skewed the results in any way. Um, Future implications that this article has on evolution is just kind of considering how big of an impact humans can have on living things with um, climate change. So, for example, here it mentions how another field that can be worked on is coral bleaching, seeing if camouflage fish are changing their patterns and if they're doing it because the coral's bleaching. But I just think it's kind of important to think about when we are doing things in our day to day life, just knowing that we're affecting others' environments too.